Before I actually get started, just checking, can you see my screen? And also, can you see my mouse?
Yes.
Yes.
Okay, perfect.
Yeah.
So let's get going then in earnest. My talk focuses on numerical relativity for binary black holes and also how it relates to all the astonishing features and successes of gravitational wave observations we had seen over the last few years. So what I do for a living is I'm running numerical relativity simulations and develop the codes for doing so. And the aspect of work that is most enjoyable is then also turning these simulations into nice visualizations like the ones showing here. But of course, the scientifically more important aspect is the calculation of the waveform that is shown at the bottom of the screen, slowly approaching merger by now. And these calculations of the waveforms as predicted by Einstein's equations are, of course, playing a very important and central role in the whole enterprise of gravitational wave astronomy. The top right inset is only a very small image of a plot that you may have already seen before. It's the very first gravitational wave detections, 1509-14, in thick lines, and right on top of it, overlaying the thick measurement lines, are the numerical relativity predictions of how the signal is expected to look like. And this has been of importance not only for the very first gravitational wave detections, but for all other since, all the approximately 100 or so of binary black holes and binary neutron stars and black hole neutron star binaries that LIGO and Virgo have been detecting, and which I'm sure you have already heard of in this conference before, as well as in other talks beforehand. To highlight the importance of waveform knowledge is very easy, because pretty much none of gravitational wave astronomy would be possible without knowing the waveforms ahead of time. For instance, the top left plot here on this panel illustrates gravitational wave template banks that are used for detection of signals via matched filtering by cross-correlating the detector output with the expected waveform templates based on general relativity. Once we have signals, parameter estimation essentially compares the measurement data with the expectations of waveforms for, say, different masses, and in this particular plot, but also of all the other parameters of the binary black holes. And you then can color code the region of parameter space where the waveform expectations agree with the measured data. And that constitutes the measurement of, say, the masses of the two objects. If you want to test general relativity, which is a really cool topic close to my heart, you can only test the predictions of general relativity if you are able to compute the predictions of general relativity. So again, waveform knowledge of what happens in GR is utterly essential. And finally, an important step that's not so often talked about are validation of all of the LIGO procedures. The example I'm showing in the bottom right panel is one takes numerical relativity waveforms with parameters close to the first event, injects them into realistic LIGO data, and then runs the LIGO analysis pipelines to recover in this case, M1, M2 posterior, both consistent with the injection, but also very similar looking to the posteriors for the actual first events. That way, confirming and validating that the whole LIGO analysis pipelines work well. There's quite a few different methods around for modeling binary black holes, depending whether you're in the early in spiral, towards the merger, or towards the ring down of the systems. Early on, the primary tool is post-Newtonian theory and reworkings into effective one-body theory, as I'm going to describe later. As you get closer to merger, the late in spiral and the merger itself, as well as the ring down, is covered by the full numerical simulations this talk is focusing on. And finally, ring down can be done with black hole perturbation theory. A second important axis I get to later is the mass ratio between equal mass binaries and extreme mass ratio binaries, where the more extreme the mass ratio is, one can also do perturbation theory in the mass ratio itself. So quite a few different tools are available. All of them are of essential use. The fact that numerical relativity is so important in this whole enterprise is that it actually covers, it's the only technique that goes from the in-spiral phase and covering the bridge into the ring down. And because of the region of parameter space being probed by numerical relativity, that region also overlays precisely the location of where the LIGO and Virgo black holes are actually happen to be placed. So NR is important in all this project. And so let me focus for a few slides and give you a few more details on numerical relativity. The subject is old. The first numerical simulations of binary black holes were attempted in 1964 by Susan Hahn and Lindquist. A lot of things happened in the early 2000s, middle 2000s. The big breakthrough happens where binary black hole simulations began to work and began to work well. And since then, a lot of more improvements have been done in order to keep up with the needs of gravitational wave data analysis and gravitational wave analysis astronomy. Let me briefly focus on these very first simulations, first by Pretorius and then by the Campanelli group and the Baker group. And these very first simulations look amazingly modest in hindsight of where we are today. You have perhaps one cycle or so of in-spiral, followed by the merger waveform, and then the ring down at the end. So the important features are there. And one of the big successes, for instance, here emphasized by Pretorius is that if you extract gravitational waves at 25, 50, 75, 100 m distance from the black holes, you get similar looking waveforms. So you're actually seeing the traveling gravitational wave shapes that are emitted. But even these very early, very first simulations already indicated a big simplicity of the merger of binary black holes, the continuous transition from in-spiral to merger, a feature that continues to underpin all of the gravitational wave modeling that we're doing today. Today, there's two well-established approaches towards simulating binary black holes. I have them here as left and right, and they go under the name of BSSN and moving punctures and Jonas harmonic and spectral. And what I find truly astonishing still is that these two approaches, they differ in basically any single choice one can make in these types of simulations. They start with radically different initial data. They use a different way of rewriting Einstein's equations in a form that is suitable for computers. On the left side, it's the so-called BSSN system, or more recently, the CC4Z system. On the right side, we're doing the Jonas harmonic evolution system. They do different things. They deal with the black holes differently. In the left approach, the black hole and its singularity is kept on the computational grid, but in a way that the singularity and the lack of accuracy near the singularity doesn't impact the simulation far away. In the right case, we excise the area inside the black hole horizon and the singularities. The methods also differ in how they pose outer boundary conditions, being fairly simple or being rather sophisticated. The two approaches differ in what numerical methods are used, finite differences versus spectral methods. In the one case, the black holes tend to advect through static grid. So if the black hole moves, it goes from grid point to grid point. In the other way, the grid actually moves along with the black hole and follows the black holes. Gravitational wave extrapolation and center of mass correction is done differently. And I'm briefly touching on one of the new features we do in our codes, Cauchy characteristic extraction, later on. So a lot of different approaches, a lot of difficulties and differences. Several groups are pursuing the left-hand side because you can use it with finite difference code and with the Einstein toolkit. The right-hand side is pursued by my SXX collaboration and using the spectral Einstein code. I'm also highlighting here a few rather important features of the two approaches in green, and most distinguishing features. Because of the choice of initial data on the left-hand side, spins are generally limited to being less than 0.9. The right-hand side can do 0.999. On the left-hand side, because the singularities remain on the grid, it turns out mergers are very, very easy to accomplish. Whereas if you do black hole excision and you want to go from two black holes with two excited spheres to one remnant black hole, this is a very difficult step. And the third major difference that I'm very proud of as well is that the high care that went into the outer boundary conditions, that went into spectral methods, that went into the moving grid, make it possible to do very long and very accurate in-spiral calculations, where our code is leading, as I'm going to show you in the next few slides as well. So I apologize for this long and dry slide with lots of words on them. Let's switch over. And,
can I ask a naive question? Sorry for interruption. Before,
absolutely.
I just curious that when you simulate this black hole, do you use the infalling coordinate or the Schwarzschild type coordinate?
We use, oh, I don't have this slide in. It turns out we use, everybody is using horizon penetrating coordinates.
I see. And
specifically coordinates that are smooth through the horizon, not like Schwarzschild, but more like, say, ingoing Eddington-Finkelstein type coordinates.
I see, I see. I'm just asking because the other side is not, physically the other side does not exist, right? The other half of your this Penrose diagram, we don't see it in nature. Means,
yes, we do not see it. Yes, absolutely. This is a good question. So if in the left-hand side here, the initial data actually starts being representative of the entire second asymptotically flat end as well.
Mm-hmm.
However, because of how the gauge conditions are being implemented very rapidly without about a light crossing time of the black hole, the left second asymptotically flat universe is lost.
Right.
And the part of the space-time actually simulated goes from our asymptotically flat end and goes up to this point here, a so-called trumpet singularity in the space-time.
I see.
So even the left-hand side here, even if I'm indicating as if it was doing both asymptotically flat ends, it actually isn't. And the right-hand side techniques here, they start with initial data that is already truncated inside the horizon, and they always only evolve the outside to begin with, staying away from the singularity entirely.
I see. Thanks.
Okay, thank you for the question. Okay, let me give you a little bit more detail about our code, the spectral Einstein code. Spectral means that we are expanding in basis functions. So we have some series in, say, Chebyshev polynomials or spherical harmonics. And the goal is to determine those expansion coefficients that multiply the basis functions to sum up to the solution itself. Basis functions work best on very simple topological shapes like a cube or a sphere. So Because of this, we actually subdivide the entire computational domain into approximately 100 or so elements. Far away, those are spherical shells. Very close by, near the black holes, these are again spherical shells. In the middle, there's complicated stuff going on with cylinders and cube to match the two inner spherical shells to the outer spherical shells. The big advantages of this setup is we can do black hole excision in the interior. We have adaptivity in that we can increase and reduce resolution in each of the elements separately. And we gain parallelizability by putting different elements on different black holes, on different processors. We further deform all our grids in order to follow precisely the shapes of the apparent horizons of the two black holes. Here's one example close to merger, where you see the black hole horizons in black here. They are quite deformed. And we have our grids adjusting to these deformations and tracking the black hole horizons. Doing this and doing it well, of course, there's a lot more technical detail involved that I'm skipping over here. We can achieve remarkably accurate and remarkably long calculations. Here's the very first flagship calculation from 2007 into 2009. You're seeing in the top left side the gravitational waveform with a linear scale and a logarithmic scale at the two panels here. At the end is the merger. And after the merger in the logarithmic scale, you see the quasi-normal ringing across about 5 orders of magnitude dynamic range. The right panel shows a convergence test for this particular simulation. Low resolution, meaning about 40 basis functions per dimension, gives us errors of about 1 to 10 radians. Cranking up resolution by only a factor 1.5 gives us an accuracy of about 0.1 radians in the merger and about 0.01 radians during the in-spiral. And it's this really fast convergence rate, the exponential convergence that is afforded by using spectral methods. This is enhanced by, to begin with, small errors that we have because of the moving grid approach that avoids advecting black holes through the grid, which would increase errors as well. So combining both together, we have this really nice and beautiful code that can handle quite long in-spirals, but that has a more difficult time near mergers. As you can already imagine, seeing this plot here, that getting all these domain deformations worked out is not an easy task. So doing all this, one important early result that I want to highlight here is a comparison to post-Newtonian theory that both serves to check that our codes are actually correct, and that also serves to quantify how accurate post-Newtonian theory actually is. And so what I'm plotting here is the difference between post-Newtonian theory and numerical relativity, where I've aligned the post-Newtonian waveform about 20 gravitational wave cycles before merger. So at that point, post-Newtonian theory and numerical relativity by construction agree, because I've aligned it there. And then you see, if you look, for instance, at the black curve, as you get closer to merger, post-Newtonian begins to disagree with numerical relativity, disagreement from 0. And also, if you go to the left, there is disagreement as well. So what this indicates that 20 cycles before merger, post-Newtonian theory at second order isn't good enough. If I'm now increasing the post-Newtonian order, you see all these curves actually converging more and more precisely on the x-axis. The deviations between NR and post-Newtonian theory to disagree, to become smaller, quantifying precisely how good post-Newtonian theory is in this particular instance, and also being an important test that our complicated numerical relativity codes actually do what one expects them to do. Of course, after the first simulations, the entire community kept on improving their codes and trying to do more accurate, longer simulations in more diverse regions of parameter space. The left panel here illustrates the entire set of 20 or so simulations that were computed by the entire worldwide collaboration in 2009. The right panel here illustrates our first SXX catalog in 2013, where from 20 simulations, we came up to 150 simulations. And we have already to show an insert if you want to actually see all the different gravitational wave cycles anymore, because the simulations also become longer. And these simulations then are used to improve analytic waveform models. An earlier EOB waveform model version 2 got replaced by an EOB model version 4, with the errors becoming smaller by about a factor of 10. And life has continued. From our collaboration, the biggest waveform catalog to take is from 2019. We have more than 2,000 waveforms. Now we are really having too many to plot individual gravitational wave cycles. So I'm resorting of plotting the parameters of each simulation. And the bottom left panel here, the mass ratio shows that most of the simulations are mass ratio 1 through 4, very few at higher mass ratios. The bottom right panel shows that most of our spins go up to 0.8, very few with spins larger than 0.8. All of our simulations are available at 3 different numerical resolutions, so we can actually assess numerical errors. And the top right panel shows a histogram of the numerical errors, typically at a mismatch of 10 to the minus 4, give or take an order of magnitude. Of course, our efforts are not the only ones, and various other groups are also doing various efforts in calculating waveform catalog. Georgia Tech and RIT are 2 other leading groups doing that, so as well as NCSA. So there's a lot of work all over the world in computing finite black hole waveforms and using them for gravitational wave applications. I'm highlighting here a few aspects. Mass ratio, if you look at the mass ratio range, typically up to 10, at most 15. Spins typically up to 0.8 or 0.9, because that's the easy part. Very precious few up to 0.998. Length of the simulations, typically below 20 or so gravitational wave cycles for the other groups, and about 40 gravitational wave cycles for us, because our code is so well suited to doing long-range projects. A few of the highlights, a few of the records. Spins up to 0.998 for equal masses. Mass ratio 1 to 128, a simulation by Lusto and Healy. The longest simulation of 350 gravitational wave cycles. There are both eccentric and precessing simulations around in the literature now, but precious few. And if you look at the years in these records, 2019, 2020, 2015, 2017, you realize all of these are a few years old. And since then, there has been a denser and improved sampling of the easy regions of parameter space. Like also I'm indicating here in our waveform catalogs, small spins, smallest mass rate, spins less than 0.8, small mass ratios. But there has been fairly little progress in the hard regions of parameter space, where hard means any combination of 2 or more of the following conditions: mass ratio bigger than 5, big black hole spin bigger than 0.9, little black hole spin bigger than 0.5, or more than about 50 gravitational wave cycles. And the overall difficulty is that the simulations are simply taking too long. All the numerical relativity simulations, the state-of-the-art ones, take about a month of wall clock time, because this is roughly as long as you can wait. And if you wanted to make seriously inroads into this blue box here, the ones would easily take a year or more or decades to run. And this simply isn't practical. For instance, these simulations up here, as short as they look, with only about, I say only, with about approximately 10 gravitational wave cycles, they had been running for the better part of a year on very big clusters. So it's difficult doing numerical relativity, and it's also difficult doing it better. Let me switch over to and briefly talk about the primary use of numerical relativity, and this is the creation of waveform models that are continuous in parameters, so you can evaluate them for any mass ratio and spin, that are fast to evaluate, that don't take a month to run, but that take only a second or millisecond to evaluate, and that also covers all the parameter space that LIGO and its brethren needs to analyze gravitational wave signals. There's three primary methods around to doing such waveform models. One of them is based on the effective one-body approach of Bonanno and Damour. And this utilizes a mapping of post-Newtonian two-body dynamics onto the geodesic motion in an effective spacetime. So using various fancy theoretical techniques and insights, one proposes a certain effective Hamiltonian where there's a free function H in here, A in here that is a post-Newtonian series. And it turns out this seemingly simple looking Hamiltonian reproduces all the post-Newtonian complexities. One adds by hand radiation reaction because the Hamiltonian would have been conservative without in-spiral. And one adds by hand a variety of free parameters all over the formalism. For instance, one adds higher order post-Newtonian terms, like in this A function. One chooses coefficients in the radiation reaction terms. One chooses the position of poles in part-degree summations for various energy fluxes. So there's tens of free parameters added all over the place. And the next step is that one now fits and fixes those free parameters against various sources of information, like, for instance, numerical relativity calculations. There's a few important benefits of the EOB formalism. One is that by construction, it is well behaved in a limit that the mass ratio goes to 0. Nu here and in the following represents the symmetric mass ratio. And this well-behavedness comes about, well, if nu goes to 0, certain terms just drop out, and what remains behind is literally just a geodesic in Schwarzschild as you want to have it. It also turns out that this resummation of post-Newtonian information into this big square root Hamiltonian increases the accuracy of the in-spiral phasing quite remarkably. The only reason we know this, by the way, is by comparing it against long and accurate numerical relativity calculations, because you need something else to compare against in order to believe what you have here in EOB. The final big advantage of EOB is that it's easy to utilize diverse information from a variety of sources. Let me switch back to the diagram of mass ratio and frequency I illustrated earlier. And let me highlight that from numerical relativity, we have the phasing and gravitational wave amplitudes of a vast number of points in the M1, M2, and spin parameter space by now. And so one can use all this information and adjust the free parameters in the EOB Hamiltonian and radiation reaction term, such that the EOB model reproduces the NR waveforms where they are available. Another thing one can do with the EOB models is one can take information from this perturbational theory in mass ratio that has, for instance, computed the first order in mass ratio corrections to the Schwarzschild periastron advance. One can now go back and check the EOB Hamiltonian and make sure that all these terms that are linear in mass ratio are such that they reproduce precisely the periastron advance. This can be used to fix more terms in the EOB Hamiltonian and just illustrates how you can use information from various sources. And so at the end of the day, this type of picture emerges. For the inspiral, you have this beautiful EOP Hamiltonian with many coefficients fitted to numerical relativity and perturbation theory. For the merger phase, ultimately, this is phenomenology that you're picking models to do the merger of the binary black holes that look precisely like numerical relativity models. And then the EOB models attach quasi-normal mode ringdowns, where the initial conditions of the quasi-normal modes are taken from numerical relativity. The relative phasing of the different modes and the relative amplitudes at the beginning of the ringdown. So you're seeing here highlighted in red that numerical relativity is all over the place here for these EOB models. The second big approach are phenomenological models that basically do away with the nice, elegant EOB formalism and directly start with sophisticated fitting formulas like the one I have in the bottom right corner here. They start with a judicious choice of the functional form, ending up with many free parameters, and those are fitted against the numerical relativity simulations, and one is done. But the big advantage is this can be done directly in the frequency domain, and one arrives at very fast models that can be evaluated in 1 millisecond thereabouts. Putting it on the parameter space map, merger, late inspiral merger and ring down is numerical relativity. Take it directly from numerical relativity. And to get longer waveforms, one attaches post-Newtonian waveforms or EOB waveforms on the left-hand side for the longer inspiral part of the waveforms, which again are informed by numerical relativity. More recently are numerical relativity surrogate models. It turns out if you take enough sophisticated applied math and you have approximately 1,000 or so numerical relativity simulations available, one can dispense of the intermediate fitting models that are needed in EOB and phenom approaches and directly take all the numerical relativity data and construct from it models by interpolating across BBH parameter space, by doing empirical time compression of the data, and doing several more quite sophisticated reduced order modeling steps. I don't have time going into this. It's an amazing procedure. Vijay Varma and collaborators are the leaders these days, taking over from Jonathan Blackman in earlier times. And all of this work is also done, many of this work is done together in collaboration with a group at University of Dartmouth around Islam and Scott Field and others. It's quite impressive work. I'm showing here one example of a numerical relativity waveform, the modeled NR surrogate waveform, and a EOB model on top of each other. And what you're seeing here is that in the inspiral, all three of them are utterly indistinguishable from each other, despite this particular case being a processing simulation where you're also seeing the processing modulations of the amplitudes. Near merger and ring down, you see the three curves do disagree from each other a little bit. And the claim to fame in this particular case for this particular surrogate paper was that the surrogate model in the dash curve actually superseded and improved on the accuracy of the EOB waveform model in blue here. And this, by the way, is the worst possible case taken from this particular paper. They actually showed one of the 2000 numerical relativity waveforms where the surrogate model had the worst mismatch with NR. It's, as I said, these techniques are truly astonishing.
Harald, a very quick question, if you don't mind.
Absolutely, please ask.
Are these simulations, they all start from R equal to 10, or I mean, what is from where do these relativity waveforms start?
This is an excellent question. The length of the numerical relativity simulations typically increases such that the runtime stays approximately at a month. If runs can be done more quickly, it's always beneficial having more cycles, so we make the waveforms longer. If certain runs would be slower because the parameters are too challenging, then we have to do them shorter. For the surrogate models, the choice was made because these are time domain surrogates. So all the simulations must cover the same time period.
Yeah, that is where my question is actually.
Yeah, here the length is chosen to be about 5,000 M for these past surrogate models, and the coming ones are chosen to be about 10,000 M in length. And this corresponds to an initial separation of approximately 10 to 12 or 15 M, depending on mass ratio.
Mm-hmm.
It's a large initial separation for comparable masses because they inspiral more quickly. It's a smaller initial separation for the high mass ratio cases because those inspiral more slowly.
Thank you so much.
You can go ahead and ask.
Hi, Harald. Very quickly, it's sort of related to Anand's point. In this inset where you show that surrogate is doing somewhat better, isn't it true that both EOB and surrogate are really here the dominant information is really coming from the NR simulations, right? So it could be that EOB did not benefit from as many waveforms that surrogates did from NR.
Absolutely. This is precisely the correct interpretation here, that this particular EOB model, this is V3, not the current V4, had a less accurate merger modeling informed by fewer numerical relativity simulations. I didn't point this out. I also didn't point out that these surrogate models, as impressive as they look in this particular plot, they are only applicable where you have numerical relativity simulations. So they only work for a time duration as long as the NR simulations. And they only work for black hole parameters, say up to mass ratio 8, where one has enough NR simulations. So if one wants to go longer, for instance, earlier in the inspiral, what one does is one attaches either post-Newtonian or EOB waveforms to the left of it. So the EOB models are still totally essential in order to cover the entire parameter space.
Thank you.
Okay, so much so far so good. Let me highlight to you 3 of the gravitational wave events, and just to illustrate that all these complexities that I've been talking about so far are actually needed and have benefits, and that it isn't still good enough, that there are limits we need to work to improve things further. The first event here is 1908-14. This is a system at very large mass ratio, about 10 to 1. And with high mass ratio, gravitational waves with all higher order modes, quadrupolar, octopolar, 16 polar, 32 polar become important. And these higher order modes information in the waveform models sharpens measurements tremendously. We can get from these wide black lines here, that happens if you only investigate with 2-2 waveform models, to these much tighter mass measurements if you analyze with higher modes and with precision. So all this extra physics does have advantages. Here's another example, 1904-12, a binary black hole with a mass ratio of about 3. And here the plot illustrates that the higher modes break the mass ratio, the distance inclination degeneracy. If you only have the 2-2 mode available, you can't distinguish inclination less than pi/2 from inclinations bigger than pi/2. You can't distinguish from phase on and phase off. And the higher modes break this degeneracy, give you a very tight inclination measurement and a much tighter distance measurement. However, this system also illustrates that the waveforms models that were available in 2020 led to different parameter inference for the system, with one of the phenom models and one of the EOB models leading to slightly different mass ratio recovery and slightly different spin measurements. Overall, it's nothing too excessively different. There's still good overlap of the 90% posteriors, but there's certainly some tension showing up here. The third event I'm showing is 1905-21, the highest mass binary black hole event detected so far. It has quite low SNR of only 15, and because it's so high mass, the signals are actually very, very short, only having 2 or 3 cycles in band. Nevertheless, despite the low SNR, which makes parameter estimation much less certain, and despite the short signal with very few cycles, which is very easy to model in numerical relativity, there are disagreements, at least some modest differences in parameter estimation. One of the 3 models shown here puts the M1 mass quite a bit higher than the other 2 models, more like 110 solar masses instead of 90 solar masses. And the models also differ in how much spin, precessional spin, they infer the 2 black holes had. That is most prominently seen in the 1p posteriors here on top, where the red is at much smaller precession spin parameter, and in particular the green infers much higher spin precession parameter than the other ones. So there are certainly noticeable differences emerging for those experts that are looking at all the data closely enough to notice them. Overall, all the big headline results are robust, no problems yet, but we are close to the edge with the current waveform models, even at current detector sensitivities. And if you go forward in time, life becomes a lot more challenging. 3rd generation detectors and LISA are going to see binary black holes at signal to noise ratios of several thousands instead of the several tens we have today. And the needed accuracy increases like 1/SNR. And especially LISA, but also the ground-based detectors are going to see a much more diverse sets of systems. So binary black holes all the way from mass ratio 1 to 10 to the 6. And one science target that actually quite scares me of LISA is the goal of measuring eccentricity to 0.1% accuracy. And this is really challenging and needs a lot of work on the eccentric waveform modeling going forward. So let me highlight in my last 15 minutes or so of my talk some of the recent NR developments. I apologize, I have been running over time, so I'll have to skip some things. On the very technical things, there are improved gravitational wave extractions being put into action that represents gravitational wave memory correctly, and that can also represent many more modes more accurately than before. Eccentricity is been receiving a tremendous amount of attention in the last 2 or 3 years so far, because generic binaries will be eccentric. In the past, waveform modeling has focused on quasi-circular binaries, because in the post-Newtonian in-spiral, eccentricity is going to be radiated away. However, there are astrophysical scenarios that could lead to eccentricities. And so we need eccentric waveform models to measure eccentricity if it's there. And if it's not there, to put upper bounds on the eccentricity so that we can say, yeah, this binary has an eccentricity less than 0.01, and that way exclude certain astrophysical formation channels. And finally, in order to distinguish deviations from general relativity from eccentricity. If tests of GR would show that we find a disagreement with quasi-circular PPH systems, then we need to check that this is an eccentric PPH system before we can claim, yeah, we need to modify GR. Some of the work we've been focusing on is, again, our long in-spiral high accuracy track. So we've been running simulations that are covering 10, 20, 30 radial oscillation periods, like you can see in this movie here, and also doing so with immense precision, having many very clean modes all the way up to the 8.8 mode. And I think very soon the simulation is going to merge, so I'll hang around on this slide to actually let you see the merger. I can point out that you might notice that by now the binary actually has circularized a lot as well during the in-spiral, as it should be. It's not just us doing eccentric binaries. The whole community is putting an immense effort in. A list of papers by various people in the community working on eccentric waveform modeling and over the last year. An eccentric waveform surrogate model showing here, as before, an R line and modeling line on top of each other. And also an eccentric UB model by Alessandro Nagar and collaborators at Jena. Again, same feature as before. All these eccentricity features of the NR waveforms are reproduced correctly in the surrogate all the way up to higher order modes. So impressive work on many fronts. Let me switch over and talk about mass ratio, and especially the range of mass ratios from equal masses like the first binary black hole event to more extreme mass ratios like the 1908-14 event at mass ratio 10 that I've been showing you. Up to here, approximately, we can do numerical relativity. On the very other end of the mass ratio range, at the extreme mass ratio range, are the extreme mass ratio in spirals. This great LIGO source, LISA source at mass ratios of, say, 1 to 10 to the 5 that are being handled with the small mass ratio approximation. But the big question in this whole picture is, what's happening in the middle? How far can you push numerical relativity? How far can you push the small mass ratio approximation? We know the sources in the middle, like in the immediate mass black holes in globular clusters, but do we actually have a method, either from left or from right, that can cover that part of parameter space? So it turns out, even if you only have numerical relativity up to mass ratio of 10 or 20, it turns out we can make statements of what's going to happen in the middle. The idea is the following. We take the expansion that's coming from the left-hand side in symmetric mass ratio, and we write, say, the orbital phasing as the small mass ratio expansion. Leading order term 1 over symmetric mass ratio, next to leading order term without mass ratio scaling, next to leading order term proportional to the mass ratio, and so on. There's more complexity I disregard, like resonances and the plunge behavior. We're just taking these first 3 terms and analyzing those. From the NR simulations up to mass ratio 10, it turns out we were able to fit phi0, phi1, and phi2 for non-spinning quasi-circular in-spirals. That plot here illustrates the 3 functions we find. There's only one function each if we have non-spinning quasi-circular and equal mass. Not equal mass. And it turns out the phi0 we find from numerical relativity agrees with the leading order small mass ratio results. The first order correction here, at the point we made this prediction, hasn't been computed by small mass ratio approximation because the calculation was too difficult. So we computed it for the very first time, the red curve here. And the other cool result we have is that the second order calculation we got some result with quite large error bars as indicated in the green shading here, but it appears that phi2, while we can't really measure how big it is, it appears to be remarkably small, very, very close to zero within our numerical errors. So what we now have is, we have phi0, we have phi1, and we know that phi2 isn't big. And so the overall implication is that the small mass ratio approximation, if one can push it to phi1, is going to be amazingly accurate because phi2 is small. So we were able to make, Martin van der Meet and myself, last year, this plot here, where distance going up, mass ratio going right. We could delineate the region of parameter space where the small mass ratio approximation at 1 PA will be good enough once 1 PA exists. Post-Newtonian is up here in that corner, numerical relativity is down here in that corner, and you see combined, they actually span the entire parameter space for quasi-circular non-spinning binaries. After we made this prediction, the first second-order mass ratio calculations came around, first for the gravitational wave energy flux, and they found this astonishing agreement between numerical relativity and second-order small mass ratio perturbation, even at equal masses. So our prediction certainly has been validated once again that small mass ratio approximations appear to be valid at remarkably large mass ratios. Some other things that are happening in numerical relativity is that myself and collaborator Mackie DC, Hannes Rüther, Adam Pound, Leo Barak, we are working on a new technique of pushing numerical relativity towards more extreme mass ratios. What makes numerical relativity there so expensive is that the small black hole that is in here, really small and not visible, unless you enlarge it, is so small. One must resolve that small black hole's scale. That leads to very small grid spacing, which leads via Courant limit to a requirement of doing very small time steps. And therefore, the smaller the small black hole, the smaller the time step, the more extreme the computational cost. The idea we are pursuing is to give up on resolving the small black hole in full numerical relativity, but rather have a volume around the small black hole, indicated here in red, in which we replace numerical relativity by a tightly perturbed black hole metric. And so we do numerical relativity up to the outer edge of this region here. That region, if you go to look at a space-time diagram, is going to excise a world tube around the small body. So that's why we call it world tube excision. We do numerical relativity only up to the radius of the world tube. And that way we can increase our Courant limit by a factor of capital R over the mass of the small body, which can be as much as 1 power of the mass ratio. So the hope is that this ultimately is going to speed up mass ratio 10 simulations by a factor of 10, and mass ratio 100 simulations by a factor of 100. We haven't done GR yet, it's complicated, but we have had success in a toy problem where we are evolving a scalar charge orbiting a Schwarzschild black hole. If we change the radius of our world tube and look at the error in our simulation, we see that the error decays with the radius of the world tube, and the rate of convergence increases the higher order we push the perturbative expansion in the interior of the world tube. If we only go to linear order in the interior, convergence rate is quite small, and we need very small world tube radius. If we go to high convergence rate, perturbative order, we can achieve a much faster convergence. And with a radius of, say, 1, get an accuracy of the solution of 10 to the minus 6, without having to resolve numerically the area within the radius of 1. So all of this looks quite good. Now let me turn to even more recent results. And this is the combination of high mass ratio and high eccentricity. So I've just showed you this cool result that we could use numerical relativity to predict and investigate how good the small mass ratio is going to be. And what I haven't highlighted was the caveat that everything I've said here only applies to non-spinning black holes and only applies to quasi-circular black holes. So given our recent effort on eccentricity, the question is, what can we say about eccentric small mass ratio approximations for non-spinning binary black holes? We did 50 great new simulations. I'm plotting a few here. They span certain orbital frequencies. Each line in this top right panel here represents one simulation. So simulations are proceeding at fixed mass ratio, of course, but for instance, this line here, it starts at some initial low frequency and proceeds towards merger, towards higher frequency. And as it spirals in, it also reduces its eccentricity towards smaller values, which is why these curves all have diagonal lines in here. So we did 50 new high quality linear simulations because we need high quality in order to make these high precision comparisons. Mass ratios up to 10. And then the next question is, how do you take now these simulations and take a limit going to the extreme mass ratio? Our first idea was, well, we have two characteristic frequencies, the orbital frequency and the frequency of the radial motion. And so let's keep those two constant because these two frequencies will identify a certain geodesic around the big Schwarzschild black hole. However, we realized that if one does this, it turns out for finite radii, finite mass ratio, the NR frequencies are often outside the range covered by geodesics. So the gray shaded area here are the ranges of frequencies geodesics take. And a lot of the NR stuff actually has stronger periastron advance and therefore cannot be mapped directly to Kerr geodesics. So what we eventually settled on is to take the orbital frequency constant in our limit and to keep the eccentricity constant. And that way we are able to map to extreme mass ratio systems. The raw data looks something like this here. So the x-axis here is the frequency. The axis to the top right is the eccentricity. And the z-axis is now the deviation from a finite Q numerical relativity simulation to extreme mass ratio. And each simulation is represented by one track of points here along the in-spiral. That data set is too complicated to work with. So what we're doing is we're picking a reference frequency, like the red plane here, and are only analyzing data on that reference frequency. That turns the 3D plot into a 2D plot. X-axis is the frequency. Y-axis, in this particular plot, I'm plotting the energy flux of the numerical relativity simulations. And now we have here 52 data points, one each for the 52 numerical relativity simulations that come at different eccentricity and that come at different mass ratio between 1 and 1 to 10, color-coded by the symmetric mass ratio here. And by the choice of a reference frequency, we have now cut each one of the long simulations into a single data point. And if you compare this to the gravitational self-force prediction, the small mass ratio approximation, which is the solid red curve here, it looks already remarkably well. We can do better though. And first take the difference between extreme mass ratio data and numerical relativity flux. And now we find, of course, very small deviations because here the difference between the data points and the red line is so minuscule. But we see very consistent trends here. We see as the mass ratio becomes more extreme, the colors of the point becomes darker, the errors become smaller, the differences become smaller, as they should, because the more extreme the mass ratio is, the more accurate the small mass ratio expansion is. We can rescale this one more time by the symmetric mass ratio. And what we find now is that all the data lies on a single curve. And I'm running through this very quickly, but this has a tremendous amount of profound consequences and insights. The first thing is that we are doing quite an extreme rescaling by symmetric mass ratio, nu cubed by now. And the only way this ever works is that the leading order small mass ratio result and numerical relativity actually agree with each other. They better should, because those are two methods computing the same thing, but it's a very important cross test, both for our numerical codes, as well as for the small mass ratio approximations, which are also really, really complicated calculations. The fact that the nu cubed rescale data collapses onto a single line as a function of eccentricity, independent of the mass ratio of our numerical relativity point, that means that we have actually, sitting here in this plot, the next to leading order small mass ratio contribution to the energy flux on eccentric orbits. This is a result that hasn't been known so far. It's computed here for the first time. Moreover, small mass ratio approximation is a continuing series in higher powers of the small mass ratio. So there should be terms proportional to nu to the fourth next to leading order. They are hardly visible here, if at all. What this means is that the next to leading order is insignificant. So we can't compute it, but the fact that we don't need it, that the points collapse so nicely, indicates that even here for the eccentric systems, the next to leading order in small mass ratio approximation isn't necessary to get really high accuracy and high precision of results. By the way, I haven't highlighted this during my talk, but all of this is also supported by quite extensive NR analysis. Here, for instance, I'm plotting the same data set not once, but 6 times for different features, different extrapolation orders, different gravitational waveform extraction techniques, different numerical resolutions of the numerical relativity ones. And all our numerical relativity choices that we have do not change the overall conclusions we have here. You see a little bit fanning out of the points. So we have definitely certain amounts of error bars around this cool looking result up here, but nothing that would invalidate the results I'm showing here. I think I'm running out of time, even if I'm accounting for having answered questions along the way. So I'm skipping hyperbolic simulations. I'm skipping an advertisement that we're also working on improved numerical relativity codes, and come directly to the conclusion and the summary of my talk. Numerical relativity is important for gravitational wave astronomy. The NR simulations in the model so far are accurate enough for the gravitational wave events so far, but all recent improvements are needed, and we're still seeing some tensions for the most extreme simulation systems. There's hard work going on to improve and to keep pace with the improvements for future gravitational wave detectors. And there's ever more accumulating evidence that second order gravitational self-force calculations will be surprisingly accurate, much more accurate than they have any right to deserve them being. Thank you very much, and I apologize for running over time.